the first two parts. What is the multi-arm bandit problem? What are its different variation? What's the main tool to privatize this? And how people do that. But then, hopefully, a few new things, not really difficult, but interesting, should be at least interesting. Lower bounds for the problem with the coupling lemma from Carl Wovedan, and an optimal algorithm for the multi-arm bandit problem, and I'll talk about them, why is it optimal. Also, this nifty side problem of the private stopping rule. And finally, maybe, a little bit of moral to the story. Okay, so let's start, motivate the problem in a real-life story. Our ingenious doctors came up with K new treatments, and now we want to determine which one is best for a certain condition. So we're faced with this stream of animated sick kids, and we want to give them an animated medicine. And we're going to do it sequentially. They're going to come one by one, non-adversarially, in an IID fashion. And we're going to choose which treatment we're going to give them, see whether they're turning into healthy animated kid or dead animated kid. And the point here is this is a sequential choice. Based on what happened in the past, I need to make a choice how to treat the next sick animated kid. Obviously, I didn't do animation here because I'm lazy and because Googling sick or dead animated kids is kind of weird. Anyway, the point is this. We have an algorithm that chooses based on the past how to treat the next patient. And then we view the outcome. Our goal is that at the end of this long sequence that has T samples, we're going to count how many people died, how many people lived. We want to minimize the number of dead. Animated dead, sorry. Apparently people are sensitive about the medical condition of tiny humans. So anyway.
Oh, what does IID mean then?
The sequence of rewards is going to be drawn independently.
Okay, even though you're basing the decision for the next child on the previous ones.
My choice, exactly, my choice depends on the history, but the reward is drawn independently each time. Okay, this is not an adversarial setting. To generalize, we are faced with these K slot machines. Each one has an arm, and I choose which one to pull. Each one is going to rob me something, hence the name multi-armed and bandits, because they're going to take some of money eventually. But each reward is drawn from its own distribution with its own mean, and my goal is to choose which arm to pull next in the next iteration, or every new day, or every new timestamp. Again, the reward, once I pull, it's only determined based on the arm that I chose to pull. Okay, my objective is to maximize the total reward over all T days. Since we are computer scientists with glue mentality, we think of minimizing the loss. How much am I losing? Because I do not know a priori what are these means. Had I known these means a priori, which arm would I choose every day? The best one, the one with the highest mean. Because I do not know, because I have to figure that out on my own, I'm incurring some loss, and we're going to look at the expected loss or the expected regret for not knowing things. That is the maximum reward that I could have gotten from a draw minus what I actually gotten from that draw when I did not pull the right arm. Okay, so this problem, despite its simplicity, is very, very ubiquitous in learning and reinforcement learning when an agent deals with an unfamiliar environment, because it's the basic problem that combines these two problems of learning, which is exploration versus exploitation. I've just pulled arm 3. I got a certain reward. Should I pull a different arm and hope to get a better reward? That will be the exploration part of my learning. I just pulled arm 3 and got a nifty reward. I want to continue pulling it because it's a pretty high reward. That will be the exploitation part. I just did something good. I want to repeat it. The way to trade the two in general is this approach, something that I read about in book. It's called Optimism. Optimism in the face of uncertainty. That is the motto for people who are dealing with these kind of problems. And let's explain one problem after another what it means. Okay, so here we are with our K bandits. We have pulled them a bunch of times. We have empirical means for the rewards we got from each pull of each arm. we are working with statisticians, and statisticians tell us that the means are not everything. We need to draw a confidence interval around that mean to tell us where the actual mean of the arm is likely to be. And what we're going to be in our optimistic approach is say, well, the best thing can happen. The best thing, the actual reward is going to be the upper confidence bound of each arm. That's what I'm going to postulate. Based on that, I'm going to pull the arm with the largest upper confidence bound. And then I pull it, and I see one of two things. Maybe it is the right arm. I should be getting a high reward. Push that confidence upper bound above. Or it's a bad arm. I should be pulling it down and then making potentially a different arm marginally better than I pull the other arm. This upper confidence bound comes from immediate bounds on the length of the confidence bound from basic statistics, 1 over the number of pulls. This is my exploration bonus. I get the actual mean, but then I'm adding up based on my optimistic approach of, yes, it'd be worthwhile to explore this arm. Turns out that this algorithm gives me the regret bound that I'm after, which is logarithmic in the length of the sequence over the suboptimality gap of each suboptimal arm. That means the difference in the mean between the actual one, the best one, and the arm that I just pulled. Now what you don't see here is basically this is squared times delta I. There's delta I squared in the denominator. That's the number of pulls of each suboptimal arms I'm going to be making. Times delta I, because each time that I pull a suboptimal arm, my loss is not 1, my loss is just this suboptimality gap. Turns out that this is also optimal. Their lower bounds match this upper bound. Okay. Let's turn to a variant of this problem, linear bandits. The main benefit of this variant is that in the previous setting, each reward tells you only on the mean of that particular arm and gives you no information about any other arms. And the basic way that people assume that pulling one arm tells me something of the reward of other arms is to put all arms in the Euclidean plane. There is some, sorry, not the plane, the Euclidean space. There is some decision set, which is a bunch of vectors in the Euclidean space. And then how is my reward drawn? Each time I choose an arm, there is some unknown vector out there, theta star, and the reward from pulling arm X is going to be the projection of the arm onto theta star, my unknown parameter, plus noise. Yet again, had we known theta star in advance, we would know what to pull in each and every time. The arm with the largest projection on theta star. We don't know, so we're facing with a regret problem. And the regret problem, summing over all time sequences, the best arm, the difference, and because of linearity, it just pushes into the dot product. Okay, what is optimism in linear bandits? Well, while there are multiple approaches, here is the more canonical one. We are going to construct a confidence set of where the unknown vector theta star is likely to be. And now we're going to be extremely optimistic. For each arm, we're going to say, what is this best vector in my confidence set that is likely to have that has the highest projection, and that will be the upper confidence bound for that arm. So we're really optimistic. We're taking for each arm a separate vector. So what is this confidence bound? The confidence bound is going to be ellipsoid. It's going to be essentially a ball, a disturbed ball, but according to some Milanobis distance. But what are these two parameters that determine the way I measure distances and the radius of this ball, or the ellipse? There is a closed formula of what will be the exploration bonus for each arm. So how do I derive this particular, the particular center of the ball, the way I measure distances and the range of that ball? Well, I do what I'm supposed to do. This theta star basically is going to be the most likely solution that gives me the prediction of these rewards that I've received. and that is solve linear regression problem. So I look at all the arms that I've pulled up to now, all the rewards that I've gotten up to now, and I solve the linear regression problem. That gives me the center of the ellipsoid set. Turns out that the center, again, has this closed form. By the inverse of this matrix times this vector, they call this matrix VT, the second moment matrix of all the features of all the arms that I've pulled thus far. And UT, the vector of the projected rewards. And the multiplication between the inverse of VT times UT gives me that center point. And moreover, VT tells me how to measure my distances, how to change the distances. So basically, if the reward is sampled from Gaussian, I'm simplifying everything, then the estimated reward versus the actual reward vector, they're going to be distributed one around the other like a certain multidimensional Gaussian, and the distance between them is going to be distributed like a chi-square. I can work out and get the right beta t. Okay? And again, you can also work out what will be the closed form expression for the upper confidence bound of each arm. The key point that I want to make, which will be relevant for the rest of the talk, is that when making this decision, all of the history depends solely on this VT, the second moment matrix of the arms that I just pulled, that I pulled up to today, and UT, the projected reward up to today. Contextual Bandit are an extension even further of this, where I'm also putting into my reinforcement learning problem an adversarial portion. That is, each person comes and tells me a certain context. My set of actions is the same set of actions, but based on the context and the action, the reward is going to be drawn. The way people model it, more often than not, is that they assume there is some feature map. They got it out of sheer inspiration. That feature map maps the context and an action to a vector, and now we have a linear bandit problem. But the key point is that every day, based on the context, I might be getting a different set of vectors. The set of actions are the same, but the mapping changes based on the context, and therefore, I'm going to get a different set of vectors. Which makes the alternative model even simpler. It's linear bandit with a changing set of actions in each day. And that set of changing action is basically provided to me by the teeth sample. The regret in this context, the expected regret, is now the maximum in each day's decision set of the same expression.
Or
Yes.
are you saying these two problems are like equivalent mathematically, or these are two generalizations of the linear problem?
Well, this doesn't say anything about linearity, but if I assume this and linearity, then they are equivalent. Okay? Because this basically tells me how I get this decision set, and this one tells me, well, someone gives me a decision set. So the context mapping is just that set of vectors ignoring the action.
And so the context is given to you. It's not something additionally you're trying to infer.
It's given to me, but it's given to me adversarially. I have no IID distribution on the context. Okay, so this concludes the intro to the reinforcement learning problem. I'm going to talk about how to make all of these algorithms for the different problems, how to make them differentially private. So the first thing I need to clarify is what is the notion of privacy I'm working with, and that is event level privacy. Okay, we're going to talk about two sequences of rewards as neighboring if they differ on the reward of a single arms pool. The privacy, however, that we want to preserve is with respect to the output of the algorithm, and the output of the algorithm is the sequence of pull throughout all days. So we want then the entire sequence, the probability of any sequence of action does not change drastically when only the reward of a single arm changes, even if that reward happened to be on day one and potentially affects the entire sequence. And the caveat here is that we're going to talk only about e to the epsilon, pure differential privacy, no epsilon delta. It's morning, let's make everything easy. Okay. Okay, how do we achieve this? Again, I told you that this is going to be boring. The tree-based mechanism of Chen et al. And Dworkin et al. It allows us to count partial sums in a stream-like fashion. But there is a purpose why I'm doing this recap. Even though I drew the tree like nature by mistake, rather than top-down, I did it bottom-up. Okay, so the idea of the tree-based mechanism, each node stores the sum of all the datums in its subtree. So in particular, this one should store a noisy count of 6, a private count of the sum of the entries below it. Note that each datum affects at most log t counters from the leaf to the root. Therefore, we need to budget our epsilon differential privacy budget goes each counter epsilon over log t. And to count what is the sum of all rewards from day 1 up to a certain day t, there is a combination of no more than log t counters that we can add up. Therefore, the variance in the count, in each count, the variance is log t squared over epsilon squared, and I'm multiplying this by log t. And if you want a union bound, then you have to add another log t. So the crux of this is that we have something that counts all partial rewards up to polylog t over epsilon error. And that's it. Basically, to privatize these problems of multi-arm bandits, you just plug in the tree-based mechanism. Okay? That is what Mishra and Takuta did, and Tussaud and Dimitrakakis did. Okay? We have the UCB algorithm. The exploration bonus is independent of the rewards that I've seen, but the main reward clearly depends on all the rewards that I've seen. What I'm going to do is to apply the tree-based mechanism to maintain a private count of that mean. And the cumulative error, if we have to maintain for each arm a tree of poly t length, it's going to be the same non-private bound plus k times our polylog over epsilon, polylog t over epsilon.
What is k?
Number of arms. It's really, really straightforward. Is there any questions about this? Are there? Okay. To apply this to the linear bandits, we do the exact same thing. Remember, we need to solve a regression problem. That regression problem is just the result of a matrix times a vector. Right, our matrix times a vector. We apply the tree-based mechanism to this matrix and to this vector. We update the confidence bound by the fact that we have noisy estimation and how much they can affect. We need some regularization. There are issues to be involved, but that's the idea. And for contextual bandit, it's also going to be the same, subject to one major caveat. Because if we want to have a differentially private algorithm that also masks the context in each day, then our regret has to be linear. There is a very simple counterexample. There are two arms, A and B. There is one context setting the reward of arm 1 to be, the reward of arm A to be 1, the reward of arm B to be 0. And there's another context that's the opposite thing. Reward of arm B is now 1, of arm A is 0. If I have to pull an arm and mask the context, I have to treat these two contexts as equally likely to appear. I have to effectively play randomized response and pull each arm with probability at least, third.
So I guess in such a setting, it seems reasonable to define your privacy as saying context comes, the arm I pull in this context can depend on this context, but must be differentially private with respect to all the previous contexts.
You want to give the talk instead of me? You're welcome. Because that's what we did. We did define the joint differential privacy based on that definition. Because the user provides the context, I'm going to pull an arm that's only going to be sent to the user. But everything that I pull to any other user, even at the end of the sequence, they come together and try to figure out what was that I told Kunal. They won't be able to. Joint differential privacy, not going to go to the formal definition, but basically, if the change happens on day t, then everything that happens on day t plus 1 till the end of the sequence remains differential. There's also the obscene E word of experiments, which we did. And we did not apply Laplace, we didn't apply epsilon differential privacy, we did epsilon delta differential privacy with different kinds of noise, different kind of instances. Basically, it works. This is the Gaussian. The lowest one is a differentially private curve. Okay, enough of the things that you already know. Now to some new stuff, hopefully. Okay, let's talk about lower bound for the private problem here. Is private UCB the best thing we can do? Does it actually meet our lower bound? I mean, how do we even go about formulating a lower bound? And here is a beautiful, beautiful tool. The Kawa-Vadan coupling lemma. We all know that if I have an algorithm which is epsilon differentially private, and there are two different data sets, D1, D2, then any event is as likely to happen on one and the other by this probability of no more e to the epsilon n. That is group privacy. That is standard result from the nascent days of differential privacy. What Kawa and Vadan showed is that if D1 and D2 are IIDs drawn from either distribution P or distribution Q, then the probability with respect to the data set now of an event changes by n times the total variation distance between P and Q. There is a beautiful coupling principle behind it that matches these two distributions such that only a fraction of total variation distance between the two are actually different samples. Okay, is this clear? The group privacy effectively shrinks by the total variation distance between P and Q. Also, and that's a beautiful observation from Celia, that this is optimal. If I consider the sampling algorithm, then basically the two distributions are different in just 1 point. So it's a different way to view amplification. I mean, if the algorithm works by sampling and then applying some, say, one differentially private algorithm, you get this result. Okay. So now here is my claim to you. My claim is that any differentially private algorithm for the multi-arm bandits, the straightforward, the simplest one with the actual bandits themselves, that is efficient. It gets sublinear regret, and the constant here doesn't really matter as long as t goes to infinity, has to pull any suboptimal arms number of times, which is log t over epsilon delta I, the suboptimality. Is the statement clear? Log of the number of samples in my stream over epsilon times the suboptimality gap. Okay? And here is the construction. There is going to be one set where the best arm has a reward of, say, half, and everything has its suboptimality gap. And then I'm going to consider arm I and pull its reward above the leading arm. It's going to have a mean reward of half plus delta I. Okay. This is distribution P, this will be distribution Q. The total variation distance between them is 2 delta I. So step one, if all the rewards of arm I are drawn from Q, the probability that I'm pulling so few samples from the right arm in this setting, the leading arm, is going to be polynomially small. And that is just Markov, because my regret is upper bounded by the probability of pulling it very few times, and each time I pull, oh, it's t over 2 times the probability, sorry. But ignore this part, ignore the latter part. The probability that I'm pulling it very few times all of the regret that I'm accumulating, which is basically linear. So if my expected regret is sublinear, that's going to be 1 over some polynomial in t, the probability of pulling an arm so few times. Then based on that, this is somewhat of a fickle argument that I don't know if I'm necessarily complicating the reasoning or not, but then we're going to decide on a hybrid argument where the first NI examples come from this distribution Q, and then I flip it to P and argue that the number of pulls is also going to be small there, and then we're applying the Kawa-Vadan lemma. Okay, so what is this hybrid model? Here's my algorithm. Rather than my algorithm going and pulling an arm, it's going to shout over a chasm, you know, hey, dear friend near arm 1, pull my arm and tell me what reward I got. It's going to be for arm 1 and all arms. And let's say that for arm I, we're going to put a special light bulb that's going to turn on after we make at least ni calls. So we just argued that when all draws of arm 1 are coming from Q, from that distribution where it's the leading arm, the probability that the light remains off is polynomially small. And because the views up to the pool ni are exactly the same, then also in this hybrid model, this is going to happen. Now notice that in the hybrid model, I have no idea what the algorithm does. Maybe it runs some weird complicated thing. Maybe it applies Rachel's detection mechanism and this senses a detection and says, okay, I'm going to stop and go solve the Riemann hypothesis. We don't know what the algorithm is supposed to do on this weird thing. But because we chose to change only the first ni pools, then the view is exactly the same up to ni with the view over a setting where everything comes from Q. And it doesn't apply if I'm changing some intermediate ni pools. That's what I find surprising for some reason. Maybe I'm overcomplicating things. Okay, and now we apply to this hybrid the Kawavadan group privacy, arguing that if on the hybrid the probability is polynomially small, then epsilon times ni times the total variation distance between p and q makes the problem of the light going off under a distribution where everything comes from p at most half. Cannot pass the threshold of half, and then we're done. Okay? Basically, it says that my expected regret has to be k log t over epsilon, because with probability of at least a half, the light goes on. I pulled it at least ni times, and each of these ni times I incurred an expected regret of delta I. And that holds for each and every arm, suboptimal. Questions? Okay. So here's where we stand. Non-privately, the UCB is optimal. It has the right upper bound that matches the lower bound. Non-privately, the additional cost, in the upper bound it's k poly log t over epsilon, and in the lower bound it's k strict log t over epsilon. And despite the fact that I'm needy, I care for the remainder of this talk about the fact that here I have a polylog and here I have a log. The added cost because of privacy, here is polylog in t and here is strict log t, and the question is which one of them is true? Hint, the lower one, the second one, that's the right upper bound also. But in order to get to an algorithm that achieves an expected regret of O of this term, of both of these terms, it should be clear based on my lengthy discussion on the tree-based mechanism that we cannot use the tree-based mechanism, at least not as is. Because as is, the standard deviation is strictly greater than log t. So it boils down to an algorithmic question. We need to change the algorithm. To what algorithm? To a different algorithm that solves the problem of multi-arm bandits, successive elimination. Also a folklore algorithm. Evendar, Manol, Mansu formalized it, but I think it was known prior to them. Basically, it works in iterations, in a round. In each round, it pulls all the arms that are still optional, still in the game, and then at the end of the round looks, has there been an arm which is noticeably suboptimal with respect to a different arm? If so, I'll eliminate it. Noticeably means twice the Hafting bound. And it does achieve the same asymptotic regret as the UCB algorithm. It's equivalent to the UCB algorithm, asymptotically. Okay, so how do we make this algorithm private? Let's start with an easier case, a thought experiment. Suppose we only have two arms. If we only have two arms, I pull arm 1, I pull arm 2, I'm basically looking at the difference of the two arms. There is an expected difference, and I want to figure out if the expected difference is positive or negative. That's my goal for k equals 2. Okay, this allows me to sidetrack into the problem of the stopping rule. In the stopping rule problem, I get an infinite length sequence of examples, sampled IID from some distribution which I do not know. My goal is to say at some point here, I'm going to stop and I'm going to output a guess, and I want my guess to be within a multiplicative 1 plus minus alpha factor of the actual mean. In particular, when alpha is half, I'm predicting whether mu is greater than 0 or smaller than 0. The key point is that I want a multiplicative approximation, not an additive approximation. And so, if mu is 0, I should go infinitely long sequence. I should take never stop. The non-private way to do that is the following non-monotonic adaptive sampling, I remember that, of Domingo et al. And it's a very simple algorithm. It basically says, I'm going to, okay, so first I have a probability of error. I'm going to decide on the infinite sequence based on this infinite sum and set my halting bound accordingly. But the point is this, I am going to halt when the magnitude of the empirical mean of all the samples that I've seen up to today is greater than the halting bound basically over alpha. And why is that? Very simple. Because the empirical mean and the actual mean differ by no more than the halting bound. And when I stop, this condition holds. I hope you can all see that. This is basically the halting condition rewarded. And when this holds, this term is no more than the magnitude of mu. And that is very simple to see because the difference is no more than the halting bound. It's upper bound by the magnitude of the difference. The difference in the magnitude of each term. Simple enough that even at 10 a.m. you should be able to see this. Okay? Questions? Okay, the sample complexity of this is basically log 1 over beta over alpha squared mu squared. And there is a different work of the Gumenal showing that this is essentially optimal. So, first thing, in order to turn successive elimination into a private successive elimination, we make this NAS algorithm to a differentially private NAS, straightforward application of the sparse vector technique. The only slight caveat that now carries a significant meaning is that we do the querying every exponentially length interval. And that actually means something when we do it with differential privacy because this reduces drastically the number of queries that we make. It actually improves the cost. Moreover, so the sample complexity only increases the added cost in addition to the cost of the halting time. The added cost in terms of the sample complexity past that original non-private halting time, I still have to wait number of samples, which is log 1 over beta over all of these other terms. And we sort of have a matching bound up to some log factors. And again, it's very simple. When one sample comes from a Bernoulli distribution of mean mu, and the other is this mu prime, which is precisely set in a way that 1 plus alpha approximation of mu prime is no good for to be at least a 1 minus alpha approximation of mu. So if I give an answer which is within the range of 1 plus minus alpha to mu prime, it cannot be a good answer to mu. And basically the lower bound also writes itself, and you get that you have to wait essentially this many steps. Okay, now with the private stopping rule, how do we solve the K multi-arm bandit for a general K? The problem is that we cannot apply the sparse vector mechanism K times because the leading arm, a sample from the leading arm, plays a role in all of these K times. And we tried various ways of getting around this, and eventually we applied this with the exponentially growing intervals and halting when one of the reviewers for the paper tells us, well, there is actually no need for the sparse vector mechanism, and that reviewer was absolutely right. So here is the solution to our problem. The solution lies in these exponentially growing intervals. Basically, what we're going to do is we're going to call these interval an epoch. We're setting the length of the epoch so that it captures any arm where the suboptimality gap is greater than 2 to the minus I. And it's very simple to see that these epochs are exponentially growing in length. They're growing by at least 4 if you look at the non-private part, but at least 2 if you look just at the private part. So what we do between epochs is that we reset all counters. We start a brand new. And that way, each reward plays a role only on a single epoch. And I do not need to budget my epsilon. I'm partitioning the data. But because of the exponentially growing intervals, well, the length of the epoch that causes me to remove an arm is basically proportional to the sum of all the length of all the epochs preceding it. So the algorithm is simple enough that it fits into a slide. It may not look so simple immediately, but it is very, very simple. All arms start at viable. I am zeroing out the mean. I'm setting my epoch accordingly, pulling all arms, setting the Hafting bound, and then I basically do private histogram. Look at the private histogram, see which arms are eliminated, remove them all, continue to the next epoch. And the analysis also fits into a slide, not really go into it, but subject to all the noise not getting out of hand, we remove any arm with a suboptimality gap, which is delta of that epoch, within a certain number of steps. And that means that the total pulls for an arm is proportional to the length of the last epoch. Yes?
What's the histogram over?
Histogram is over the reward of all the arms, of the K arms. Or the remaining viable arms, sorry.
Active arms. Oh, okay.
More questions? Okay, now the key point is, as ever, because we want the expected regret, we have to set beta as 1 over t. So everything that was log 1 over beta becomes log t. So the total regret is log t. That is the source. Log 1 over beta, beta being 1 over t, that's the source of log t. 1 over the suboptimality gap of this arm times plus 1 over epsilon. And when you sum over all k, you get the matching non-private regret bound and the private regret bound. And again, we also did experiments. These are actually the experiments with our earlier version of this algorithm. But what's nice about this is that you point out the shift. You should compare all the solids among themselves and all the dotted among themselves. So this is the private UCB algorithm. And notice the smooth shape of it versus the successive elimination problem. And notice how sharp it is. Basically hits a point, up to a certain point, I'm pulling arms, pulling arms, pulling arms. Then I've removed them, then they're no longer viable. So it flattens out. At least I find it interesting when the experiments back up the math. Okay. How much?
2 to 3.
Oh, great. Because I'm going to skip to the part I talked about in terms of moral. Not that I'm any qualified person to talk about morality, but and again, these are only my 2 cents, so please don't attribute anything to the math here. High-level overview. There are 2 algorithms, UCB and successive elimination, that are equivalent non-privately. They have the same regret bound, and they're both optimal. And yet, when we make them differentially private, one is noticeably better than the other. And why is that? So first, I rearranged the slide. I was sure I saved it. Okay, so maybe ignore this part. But here's a question to you. Must it be like this? First is my question to you. Is the tree-based algorithm optimal? We know that the lower bound, again, for the tree-based algorithm is log t. We don't know it has to be polylog t. We just know that it doesn't meet the requirement. But even in an adversarial setting, can we argue that it's strictly polylog t and not log t? Now, assuming this appeared before this, why are the 2 algorithms different when I do the cost of differential privacy? It's because of data dependence. The UCB algorithm makes a data-dependent choice each and every day. Looks at the upper confidence bound. I pull this arm, oh, now this now is slightly better, I pull this one. It makes a data-dependent choice each and every day. Whereas successive elimination has basically only k-1 meaningful days in which it declares, I don't want to pull arm 17 anymore. I don't want to pull arm 33 anymore. And only if you know these days, the rest of what the algorithm pulls is obvious, sequentially each arm after another. So we can think of it as successive elimination being more simple than the UCB algorithm, and differential privacy as a tool that prefers simplicity, that puts a quantitative price to being simple. And I'm asking, is this phenomena occurs in other data analysis tests? I would be very curious to see that. And secondly, can we somehow measure simplicity in a way that's effective, that a way that's going to tell me, oh, at least for differential privacy, this is going to be better. So this is the elegant way of looking at it. Here's the uglier way of looking at it. The uglier way of looking at it is to say, well, this successive elimination algorithm is lazier than the UCB. It doesn't make a decision until it gets an overwhelming evidence telling it that this arm is bad. Only there it declares, oh, you know what, I'm not going to pull that arm. I've pulled it enough. I know that it's going to be bad. So could it be that we are, as differentially private the algorithm designers, prefer laziness? Should we change the motto into laziness in the face of uncertainty because that costs us less? With this model, I'll conclude. The bibliography of all of those works, not very long. You're welcome to read it.
Reflecting on your last slide there, I guess one cost of these Bandit-style adaptive data gathering algorithms is that there's a sort of a bias introduced in the estimates that they produce in terms of their actually, Aaron could probably provide a more precise statement, but effectively they end up providing biased estimates for the arms that end up being dropped early because they, basically there's sort of a selection effect where they tend to drop arms where they underestimated the mean. And
in the classic multi-arm bandits?
Yeah, actually. So if you think of it as sort of as doing multiple things, and one of them is to just produce estimates for the means of each of the arms at the end of the algorithm, in addition to the task it's normally trying to do.
Yes.
Then it tends to without modification, they tend to underestimate the bias of the. They tend to produce biased estimates for the arms that get dropped early. And so there are like simple fixes to this that involve sort of gathering kind of twice as much data or something like that. But I wonder if that's sort of a place where simplicity provides an advantage, like a demonstrable advantage. I don't know if...
Yeah, well, I mean, I guess even just the argument that Aura just gave us that you can describe the entire transcript.
Right.
But just these case steps gives already a compression bound. Yeah, it seems like yes.
I have to say that I don't see off the top of my head the relation between the compression and the bias, but...
So if adaptive data analysis works, there's a link that's made between description length of the output, how much bias that tells you, gives you some limitation on how much it skews conditional probabilities. That's, I think, what Aaron is referring to.
Let's thank Oregon.